Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends at Linode. With 200 gigabit private networking, scalable shared block storage, speedy SSDs, and a 40 gigabit public network, you get everything you need to run a fast, reliable, and bulletproof data platform. And if you need global distribution, they've got that covered too with worldwide data centers, including new ones in Toronto and one opening in Mumbai at the end of the year. And for your machine learning workloads, they just announced dedicated CPU instances, where you get to take advantage of their blazing fast compute units. Go to dataengineeringpodcast.com/Linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. And to keep track of how your team is progressing on building new pipelines and tuning their workflows, you need a project management system designed by engineers for engineers. Clubhouse lets you craft a workflow that fits your style, including per-team tasks, cross-project epics, a large suite of pre-built integrations, and a simple API for crafting your own. With such an intuitive tool, it's easy to make sure that everyone in the business is on the same page, and Data Engineering Podcast listeners get 2 months free on any plan by going to dataengineeringpodcast.com/clubhouse today and signing up for a free trial. Support the show and get your data projects in order. And you listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, and the Open Data Science Conference, and coming up this fall are the combined events of Graphorum and the Data Architecture Summit in Chicago. The agendas have been announced, and Super Early Bird registration is available until July 26th for up to $300 off. Or you can get the early bird pricing until August 30th for $200 off your ticket. Use the code BNLLC to get an additional 10% off any pass when you register. And go to dataengineeringpodcast.com/conferences to learn more and to take advantage of our partner discounts when you register for this and other events. And you can go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers. Your host is Tobias Macy, and today I'm interviewing Stepan Pushkarev about Hydrosphere, the first open-source platform for data science and machine learning management automation. So, Stepan, could you start by introducing yourself?
Hey, Tobias. Thanks for the intro. My name is Stepan Pushkarev. I'm CTO of Hydrosphere, machine learning management platform. My personal background is in data engineering, backend engineering, and I've spent a couple of years working closely with machine learning engineers and delivering the stuff to production and to life. So that's my background.
And do you remember how you first got involved in the area of data management?
So I do not remember exactly. It was probably the earlier versions of Spark back to 2016, probably not 16, or even like 14. I don't remember exactly. So it's kind of all the software engineering world and especially designing and building distributed systems evolved, and basically major stuff that we've been working on are databases, data integrations, and it was very smooth transition from the classical software development to so-called big data software development. So it's now it's not a buzzword anymore, but early Hadoop and Spark days, it was very cool to deal with.
And so, for anybody who hasn't listened to it yet, you and I talked a little bit about your work at Hydrosphere. I think it was 2 years ago now at the Open Data Science Conference, and I'll add a link to to our conversation there in the show notes. But wondering if you can just start by giving an overview about what it is that Hydrosphere is and some of the origin story of how it got started and your motivation for getting involved with it.
Yeah, sure. So back to 2016, I guess. I wrote an interesting blog post on KD Nuggets. It was the topic was big data science expectations versus reality, and it was kind of manifesto of what we've been working on, and it was on very, very high level, just some notes that hey guys, you're like hey community, you're talking about the all that benefits of machine learning and analytics, but what is a reality? And the key take there were a few takeaways out of those blog posts. First one was tools evolution, that existing tools in machine learning are great, but not stable and user friendly, and we will certainly see a rise of new tools that will augment machine learning engineer and data engineer in the future. The second takeaway was education and cross skills. So when data scientists write code, they need to think not just about abstractions, but need to consider the practical issues of what is possible and what is reasonable. So, and the third takeaway was that improve the process. So DevOps might be a solution in terms of the machine learning lifecycle, machine learning workflow. It was a very windy definition, and I was trying to play with the some maybe coin some name and define those value proposition, and getting some feedback from the community. But if you now, it may seem very obvious for people nowadays, because the community has grown, and big companies, the major players, have evangelized a lot of cool and good stuff. So but anyway, 3 years ago it was kind of new, and we were looking for a community, we were looking for traction and some feedback. And the reason I was trying to share those notes and thoughts, that we've been working on some cool projects on a consulting basis, but our parent company, where I'm also part of, is a machine learning consultancy and solutions provider. And we had to deliver the stuff to production for our clients to make it work 24/7. And as far as we were contractually obligated to deliver stuff to production, we had to invent all that stuff for ourselves and automate our own process to decrease our overhead and to automate our routine work. So we started just building some DevOps-like tools for not a continuous delivery, continuous integration, but some minor stuff that will help us to move faster, to close that gap between training and retraining, and make things more user friendly for our internal users, for data scientists and machine learning engineers. So from that very wide idea of, hey, let's do something cool and let's automate our own process, we thought it may make sense to find a new niche and open source this project, and start a new website, start a new GitHub repo, and start talking to people and getting some traction. So that was a story. We evolved. After that ODSC in Boston, when we met first time, we got some good traction, and it was kind of test of the water, and it was our very first public conference then where we participated in. I got some good feedback, and since that time we think that space is currently even categorized by Gartner. It means that it's already here, it's already there. You should take a look at this. Enterprises and big and small companies should take a look and consider this model management in their day-to-day operations.
And in your experience of building and maintaining Hydrosphere and working on consulting for people who are getting involved in machine learning, I'm wondering what you have found to be some of the most challenging or complicated aspects of managing those model deployments and managing machine learning in a production environment. And if you can provide a bit of compare and contrast to how that relates to more traditional software life cycles of deploying and managing production environments for software applications.
Yeah, sure. So I would rate the first, probably the most challenging part is dealing with exceptions, edge cases, and certain blank areas of the model. Most of the data science teams are not there yet, but anyway, so it's something I need to mention. Another, like in a software engineering world itself, and as well as in machine learning world, so dealing with state, with the model state. For instance, if your model is stateful, it's obviously really challenging to scale it horizontally and so on. So it's kind of another issue. And as far as you do not control this code, you cannot make it really scalable enough. Dealing with APIs integration it's also kind of inherited from the software engineering world, but slightly changed, slightly different in machine learning. Even like array-based API versus named array is kind of such a small things, but that makes they make integrations really hard. When data scientists exposed an API of 200 features in just an array, and you should just remember the index position of a particular field to pass the parameters in and expect the same array as an output, is kind of useless for software engineer who expects a nice JSON API with a named features, named parameters there. So it's kind of cultural, but usually it creates a lot of like chaos in an integration pipeline. So yeah, but as I mentioned, but probably the first and the main and major challenge at this moment is iterating with the model and dealing with the new concepts and new exceptions that you face in production. Even I would like to mention the example. We've been working during last week on a nice demo for a conference with the hard hats. It was just a demo for the manufacturing conference when we, on a consulting basis, when we provide safety control based on the computer vision for manufacturing sites and construction sites. So you can, if you wear a hard hat and you wear gloves and so on. So we basically let you in or deny an access. And while working on this, of course, there are a lot of like open source data sets, public data sets to train with. There are like ready off the shelf machine learning models. You can quickly, within a couple of days, hack a prototype. You can hack a pretty decent machine learning model that can recognize person in hard hat and person without hard hat. It can even authenticate that person and so on and so on. But obviously, when we started testing this model, it's really easy to fool the model. For instance, if you just take off your hard hat and place it somewhere in your shoulder, it's easy. It's the model recognizes you in a like recognizes a safe access. So it's kind of, and there are many other tricks you can make, obviously, to fool the model. So when we started to iterating, we started just adding this edge cases, and when you test it, even within like a group of 5 people, it's really challenging to track all those edge cases and aggregate it into a new retraining batch and like basically automate this process to iterate quickly. So obviously that like deploying on Hydrosphere, that our own tool made our process much easier. We even within this small group, we were able to like make the model reliable and stable relatively quickly. So obviously when we will deploy the model to production, there will be much more edge cases that we will automatically gather and like incorporate it into our training, retraining, and testing pipeline, so we will not miss it in the future.
And so for anybody who's not familiar with Hydrosphere in particular, can you just outline the overall design and architecture of the platform and talk through the different components and how they fit together?
Sure, sure. So yeah, by the way, we're open source. You can check it out on a GitHub. Dig a little. There is nice documentation. It's user documentation, but we can dig into the source code as well. So we are primarily Scala guys, Scala and JVM guys. So Scala, Akka, microservices, a couple of databases for different purposes. Postgres for relational data. We store metrics in InfluxDB. We store inputs and outputs of each model in a raw format in a RocksDB. If you're not familiar, RocksDB is something that Apache Kafka is Kafka streams using on the back end. So yeah, Docker obviously for and the Kubernetes for deployment and orchestration. A couple of like Python microservices, CLI, and Python runtimes for machine learning models. We extensively use streams. We switched from Kafka streams to Akka streams just because we need a dynamic kind of our models that could be added in runtime and deleted in runtime and so on. And the Kafka topics are not designed to deal with this type of this type of environment, this type of use case. We use Akka topics, Akka streams. Sorry, but yeah, in general, those are main keywords and main technologies we use.
And as far as the different pieces of Hydrosphere, I know that you've got the serving layer and then you've got the metrics layer for being able to determine the overall health of the model in production. So I'm curious if you can just talk through maybe what the different concerns are for those pieces and how they tie together to fit into what the overall workflow would look like for somebody actually building and deploying and managing their model in production, and how it simplifies the overall process versus what a homegrown solution might look like.
Yeah, everything starts with model cataloging and model deployment. So once the model has been built, we basically hook into the training output to the binaries produced by training pipeline. It might be a pickle file. It might be the protobuf file for TensorFlow or other formats like Keras, PyTorch, and others. We hook it into this pipeline and basically upload the binaries to our service, and we extract all the metadata from out of those binary formats and generate additional metadata by hooking into that training pipeline. We capture training hyperparameters. We capture all those characteristics of training data, its distribution, its all other statistics, and a whole bunch of other metadata that might be useful for downstream applications to use and to trace the request and trace the root cause of any other or any prediction. So we catalogize the models. We build the Docker containers and store it, the Docker images, and store it in Docker registry. And for us, machine learning models are immutable Docker images that could not be modified, obviously. And this is the way for us to do versioning. So our versions are not just an index, a number in database. It's kind of physically packaged machine learning model with all the dependencies and all the metadata. So the next step is basically serving. When by serving we mean a deployment of Docker container in a runtime environment. You can deploy the model in different type of runtimes. For instance, different versions of TensorFlow, different versions of like other libraries, or just tweak some runtime parameters to be more like to gain more latency and to gain latency and so on. That's a typical microservices architecture. So we launch and orchestrate this Docker containers using Kubernetes API or Amazon ECS API. It's kind of just well integrated and well orchestrated platform. But we do not reinvent the wheel here. It's just a classical, well implemented architecture, microservices architecture. The second piece of our, the second major part of our platform is we call it Sonar. So Sonar is also a couple of microservices that shadow or mirror the traffic from the main prediction pipeline and do all the magic with analysis of inputs and outputs, analysis of the model health, and monitoring the models. Basically, we monitor a lot of basically we monitor almost everything that is related to machine learning model, and it happens kind of automatically. We generate a whole bunch of statistics, we generate a whole bunch of metrics, and we have a user-defined metrics that you can basically monitor a particular output, for instance, a confidence of machine learning model, and assign a threshold to deal with, and to alert when your confidence of machine learning of your predictions are below a particular threshold. Yeah, and those like Sonar part is all based on streaming. We analyze, we calculate all the distribution, we calculate all the histograms and data profiles on the fly. This may not be explicitly required by the use cases. I mean that the model may not degrade so quickly, so we do not need a real timeless here. But this design consideration has been made just because it's the streaming here is much more convenient from the operational standpoint. You fail fast if you cannot process data. You fail fast. You can easily recover. You can easily replay what you have not processed. It is a concept of just fast data versus big data. So if you do not process data when it arrives, you will likely not process it later. So and there is a lot of IP in that like Sonar part. So there are some sophisticated machine learning models like generative adversarial networks, some variations of autoencoders that are designed to profile and monitor your production traffic for anomalies, for edge cases, and basically to provide the insights into your further iterations and machine learning lifecycle, so you can retrain and subsample and retrain subsample data and retrain machine learning models easily.
And I like what you were saying about the fast data versus big data when it comes to managing the metrics for the models, because I imagine that, particularly depending on the problem domain that you're working in, but some of those alerts might be very time sensitive in terms of knowing when you need to adjust the parameters for the model, or maybe roll it back or revert it, or rerun the training process to ensure that you can correct for some of that model drift. And so I'm wondering if you can dig a bit more into sort of how you collect some of those metrics and the types of information that you're looking at for signals to let you know when you need to take some sort of corrective action for the models that you're managing and that are currently being served and providing information back to end users.
Yep. And this is, of course, there are different use cases. In some of the use cases, you may not even have a data drift at all. For instance, if there is a classical collaborative filtering for recommendation systems, basically the training in a batch mode, that where the training is happening right before the prediction job. So it's not the case. But there are cases when there is a drift, but it's kind of slow drift that your user behavior is being changed over time, and you can recalculate some metrics overnight. And that's also okay. But if you take a user experience in a consideration when you deploy the model, and you will need to watch the model health in the next like 10 minutes, the next like 15 minutes, just to make a sanity check. Okay, it's working well. So we basically need the real-time metrics. And as I mentioned, we analyze it in Akka streams. Sorry, yeah. And what we do, we trace, of course, all the route of the prediction request through the models. There might be much more than there might be more than one model in a pipeline, and we attribute each request with the necessary metadata to be stored. And we store all the requests, and we store all the predictions for the auditability and for discoverability purposes. For instance, if you have a high-level metric that, hey, your some data distribution has changed, you will, as a machine learning engineer, you will need to dig a bit deeper and deeper to a particular request that or sample request that caused this data drift. For instance, in a very toy example demo that we're running, that we demonstrating, if you trained your machine learning models on classical Manis data set, and all of a sudden you start sending letters instead of digits, you will need to get an alert, then click on this alert, drill down into details, see, okay, something is going wrong, and you will need to see a particular request that caused that alert, or the alert might be caused not just by a particular request, it might be caused by like 1,000 of requests, and you will need a relevant user experience, so it needs to be done in kind of near real-time way. So and then if you so you have that a particular prediction, you will need a chance to trace it back to machine learning model version, to all the to machine learning prediction and training pipeline, to the original data set that machine learning has been trained with, for the same, for auditability and for the ability to make a decision for retraining or reconfiguration or maybe hyperparameters tuning. So basically each request has a full information about the data set it has been trained with, hyperparameters it has been trained with, deployment configuration, and all the metadata that might be relevant for this particular prediction. That's kind of cool, the main value proposition for end user that we're proud of.
And you highlighted a couple of things there that can contribute to the overall model drift or model degradation in terms of changes in the usage patterns for end users or changes to some of the input data. But I'm wondering if you can just talk through in general some of the factors that will contribute to that sort of model drift, and any type of contextual information that you're monitoring and alerting can feed back to the data scientists or data engineers or machine learning engineers to understand what alterations to make in the training process to correct for that, and just some of the overall contextual knowledge that's necessary to be able to engineer in sort of resistance or just tightening the feedback loop for keeping those models in proper working order and ensuring that they're doing what they're intended to do?
I think the first and the most frequent use case is just not enough training data, or not well architectured that retraining pipeline. So usually data scientists are being provided with a data set that they play with, and that's it. So they iterate theirs in their laboratory environment, and then there is kind of training serving data skew. It's what I see. It's one of the most, from the one hand, one of the most simple reasons of it's not a degradation. It's just organizational and architectural reason of having machine learning model deployed, trained with on a bit different data set than you expect in production. So, and it's actually it's interesting use case because it obviously demonstrates that machine learning models and machine learning environment in production needs to be designed to be tolerant for this type of use cases from the very, very beginning. Another typical reason of inconsistency between training and serving data is just the enterprise-wide environment. When you deploy a particular model and you have more than one consumer of this model, or one of more like department, or one of more teams that are using this model, and some of the teams may misinterpret your API and will start sending will start using this model just for a different use case. It's also the case. It's nothing to deal with the concept drift. It's more just organizational and use case drift. As an owner of this service, you will need to be notified that, hey, your end user is trying to classify something else, or you're starting to extract the information from a very different text and that has been used for a very different domain, for instance. And another use cases that are just really frequently changing environment in IoT, in deployment of new type of sensors, deployment of new type of locations. That's really the case. And actually, most of the computer vision and text applications, they require this type of iterative approach for discovering new concepts, and it's not a drift. It's kind of expected behavior. Hey, you're discovering. It's just a part of your system. That's probably it from my side. Yeah.
And another thing that I was interested in when you were discussing some of the metrics collection is what you were saying around having that be useful for being able to sort of revisit the overall path and trace of the interaction of data flow through the model to understand what were the inputs and what were the outputs, for being able to retroactively evaluate what the decision-making process was like, so that for cases such as GDPR, where you need to be able to say why a particular decision was reached in a machine learning context. And so I'm wondering sort of how the Sonar component fits into that type of regulatory environment, or some of the other interesting insights that are able to be surfaced by going through that information.
Yeah, this is kind of must-have feature of all the enterprises, that you need to store all the predictions, and you need to be able to trace back to the origins, to the exact data set that has been used for the model to train. And I'm not sure about GDPR. I'm not super familiar with that particular requirement from GDPR. But it seems kind of must have requirement for any enterprise that, and not even enterprise, it's a requirement for any type of organization that is trying to deploy machine learning models to production. And the one thing is just to store requests and responses and save it to somewhere on an S3. And another thing is to make it really useful for users, for business users, and for machine learning engineers to use it for either for discovery purposes, either for like audit purposes. Basically, you need to store it in a queryable format and to be able to be visualized and gather some like statistics out of it. And if you will think about this, it will if you will think about this further, it will become your ground truth feature store, well discovered with all the discoverability features, with all that nice stuff that will become eventually your main data repository within enterprise. So it kind of flips that paradigm when you have a training pipeline kind of separated from the rest of the production, and it's just a query to your database, and data scientists and machine learning engineers to place somewhere on a side with the data and train the models and then push to production. And when you start like blurring the line between that type of offline environment for machine learning experimentation and online environment, you will see that the online, always up to date, always always fresh feature store that has been built right from the production traffic, and which that is well discovered, well indexed, is kind of the main asset you have in enterprise. So it's kind of an interesting observation that I see more and more in organizations. So it's we'll see where it goes to.
And as far as the state of the sort of level of sophistication of different organizations and the available tooling for managing machine learning projects in production, I'm wondering if you can sort of give some background about where things were when you first started work on Hydrosphere and how the overall ecosystem has evolved since then, and how that has impacted your overall approach to the design and development of Hydrosphere itself.
Yeah, originally it was, as I mentioned, I've been writing some like blog posts, trying to coin the names and trying to explain different type of people that it's something that is gonna be probably not the next big thing, but it's definitely a niche. Yeah, last year we've seen Google has published a nice paper about the missing gap in machine learning ecosystem. Other great tools like Kubeflow, TensorFlow Extended, MLflow, and many others emerged. And this really helps to explain people what it does and why especially the why aspect of the things we're building. So it definitely accelerates the education and the community growth. I mentioned Kubeflow and MLflow. That's two tools has similar names but slightly different purposes, and in my opinion they really add value to that ecosystem. Probably MLflow is for me is a bit more mature project, driven by Databricks and Microsoft now. It has more value add contribution to the end user. So you can just, for those who are not familiar, MLflow is a tool for experiments tracking, and it's one major part I think of this tool is experiments tracking. So you can basically track all your runs, all your experiments, all the metrics also, and all the outputs and inputs and your like hyperparameters and other stuff in a collaborative way, so you can share it with your manager, you can share it with your team, and basically also very interesting, you can use it for auditability of your training pipelines, so you can prove anytime what data your models has been trained with, and so on and so on. It's a Python based. It's kind of easy to start, easy to play with. Has a nice like and very precise use case. Kubeflow is a bit wider project. Started as the way to deploy TensorFlow on Kubernetes. Obviously, like Kubeflow is driving users to Kubernetes ecosystem and trying to become just own that territory of machine learning on Kubernetes. And I think the main value add product that they has released recently is Kubeflow pipelines. It's basically an abstraction, the Python DSL on top of Argo pipelines. Argo is a tool on Kubernetes native GitOps tool. So there are a lot of buzzwords, but it's all the new stuff that the community is learning now. So you can, in a very, very simple way, on a high level, you can think it as a new Jenkins, Kubernetes native Jenkins, and for defining this continuous delivery pipelines and deployment pipelines. I will not go into details. So of course, some like DevOps people and infrastructure people and Kubernetes guys will disagree with me, but there is something to discuss there. So and Kubeflow pipelines are kind of Python DSL on top of that. It is still not as mature as Jenkins, for instance, as Airflow, but it is and it is still not. It doesn't add any particular value into machine learning space. So it's supposed to have a machine learning specifics, but it has a little at this moment. You can visualize machine learning like you can visualize your steps outputs in a way that is in a way it is well received in the data science community. For instance, you can visualize a precision recall, you can visualize a confusion matrix of a particular training pipeline, a training step, and basically have it as an output. You can have a tensor board attached to the logs of your training pipeline, so it's kind of a nice integration with those tools. But still, for instance, there some users, some like experienced users that are has some experience with Airflow type of tools, with Jenkins type of like CI/CD tools. They will find it as a very, very new project. I think if you will take a look at their roadmap, they will be adding really cool features that are machine learning specifics, machine learning related. So it's you should stay tuned. But at this moment, it's kind of, I would say it's more in experimentation phase. You will write more code, and you still write a lot of boilerplate code to define Kubeflow pipelines, pass the parameters in and parse the outputs of those of this like pipeline steps. Each step, obviously, in Kubeflow, in Kubernetes world, is a separate Docker container, and like basically defining these steps is kind of, there's an overhead right now, a usability overhead, but overall, I think it's kind of, it forces users to do it in a right way. By the time the Kubeflow community Kubeflow team will add more user-friendly DSL and user-friendly abstractions and the features into their DSL, it will become more useful for users. And yeah, for we are really looking at this ecosystem, evolving ecosystem, and building integrations with Kubeflow and MLflow, and also with some proprietary cloud Azure and AWS services like SageMaker, etc. So this ecosystem, of course, evolving. We're part of this ecosystem and trying to be as much as close into this community.
And as the availability of different tooling and the overall level of understanding and sophistication of practitioners in the field has grown in the past few years, I'm wondering how that has influenced overall design and architecture of Hydrosphere and some of the types of tooling or platforms that are often used in conjunction with Hydrosphere, and how that might break down across the different sort of roles across the data team as far as data engineer versus data scientist or machine learning engineer.
Yeah, so our own architecture has not changed on a high level. High level architecture has not changed from the very beginning. We have, as I mentioned, replaced some like Kafka with Kafka streams with Akka streams. We've been using heavily Envoy and Istio for traffic management and traffic routing between models and other microservices. We switched to another implementation recently with some with our own add-ons into that process, just because the Envoy is not designed to handle machine learning specifics routing. When you need, for instance, you need A/B testing. We call it response-based A/B testing. When you make it you route 100% of the traffic to model A and 100% of the traffic to model B, and then have a kind of aggregator that will not aggregator, that kind of controller that decide what response to return back to user A or B. So it's like response-based routing and some other interesting features that are really required in machine learning. We switched to our own implementation of that. We started contributing into Envoy, but then we saw that it's so too far from what we need, and we do not have any influence in the community there. So it was easier for us to build the features ourselves. In terms of other tools and ecosystems, of course, evolving. Cloud providers, they are part of the innovation, and Azure is doing a great job on also simplifying deployment and serving machine learning models. They also have some monitoring stuff that might be comparable with the features that we offer to some extent. SageMaker is a bit behind this monitoring stuff. They have not even. I don't think they have. Obviously, they thought about this, but to the best of my knowledge, it's not on their roadmap at this moment. Though the cloud providers are innovators, open source ecosystem is also cool. Datasets versioning tooling is kind of quite popular at this moment, and there are interesting discussions in the community. We had the discussion to integrate with DVC. Yes, I don't misspell them. Datasets versioning tools, but then we decided that if you architect your data platform in the right way, so you have immutable data sets, and all the versioning of data sets could be done just by having immutability in your data. So a query to immutable data set should always return the same result over time. So, and basically this query is a version of your data set. So it could be done without any additional toolings, and now we use it extensively on our own projects and our own implementations. So But it's also an interesting topic to be discussed. How to version your data sets. We just take away. Yes, there are tools, Git-like tools for versioning data sets. But first of all, you can do it you can do it without a special like tool for that, just by proper architecture and design of your data sets and databases, and having your training data sets immutable by design. And first of all, if you still need it, there are great tools that you can utilize, and that capture all that interesting, also capture all that interesting metadata, and store that metadata alongside with your data set.
And when you first began working on Hydrosphere and got further into the problem domain, I'm wondering if you can talk through what your original assumptions were going into the project and how they have been challenged and updated in the process of building and growing the platform and getting more involved in the machine learning ecosystem.
Yeah, of course. So, as I mentioned from the very beginning, it was our design and our main value proposition has been based just on our own experience, and that wasn't a purely academic research. Of course, it was a real life integrations. But the major kind of thing for us is a feedback from users. For instance, if we talk to the customers and they do not select our platform for their business for particular reason, that we're missing some features or missing some integrations, it basically facilitates all that developments and all that development / product / marketing efforts. Currently, what we've learned, this auditability and observability of machine learning predictions, and auditability of machine learning pipelines, including training pipeline and serving pipeline, is kind of must-have. This is a feature that we haven't thought from the very beginning, but we have added that recently. Also, the technology is evolving, so explainability of machine learning models, there are new tools and new research. Adversarial networks. When we started, there was no the generative adversarial networks didn't exist. So we basically scraping all the latest and greatest from the research, and which is applicable to our main goal and main value proposition. For instance, we do have machine monitoring models that monitor that data drifts, and they are neural networks, and obviously it's challenging to explain why a particular request has been highlighted as an anomaly or as an edge case. And we added that explainability feature, that we explain our own predictions, explain our own judgments, and can, of course, explain it to the end user. Say, hey, we see you have some you have a concept drift, and this is the reason of your concept drift, that the particular feature has drifted to that way, to that direction. So it's also cool, and we can really helps to our main mission and vision to provide the instant feedback loop for data scientists and machine learning engineers, so he can iterate quickly in production, not just in research, but in production.
And in terms of the future of Hydrosphere and your experience in the space so far, I'm wondering what you have planned in the future for the platform, and anything that you're keeping a close eye on in terms of ongoing developments within the community and the overall ecosystem.
Yeah, so Our main goal for the next quarter is integrations, and there is something that we're very feature-rich platform. There are a lot of features, a lot of like product features. What we're missing currently is integrations with cloud providers, integrations with OpenShift ecosystem, with Kubeflow and all that. So we will be. It includes not just development of those integrations. It also includes documentation, tutorials, and blog posts for that. So it's our main go-to-market strategy at this moment.
And are there any other aspects of the Hydrosphere platform or the overall concerns of managing machine learning projects in production and tracking and maintaining upkeep of the overall health that we didn't discuss yet that you'd like to cover before we close out the show?
I don't think we have covered pretty much everything that I had in mind. We can talk about different topics, but I'm not sure it will be relevant for this show. I have a lot of stuff on streaming. We are just streaming versus batch and all that ecosystem, Kafka and stuff. It's not relevant at all to machine learning management, but I would be happy to elaborate on that as well.
Okay. Yeah, I mean, that sounds like it could probably be a whole nother episode on its own. So I'll have to have you back on to dig deep into that whole problem space and your thoughts there. So for this topic, I suppose we'll call it a win. And so for anybody who wants to get in touch with you or follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd just like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Wow, it's a pretty wide question. So everything that is related to production, and I think we have a pretty decent tooling and for research, and but even for research, when you train your machine learning model and it's being trained for like overnight and for a couple of hours, and if your performance is being if you're tracking a training performance, a TensorBoard interface, but with more precise and more metrics-rich information, which may make even decisions on your training performance and maybe stop it or retune it. It's kind of a big topic. There are cool projects and cool vendors that are also looking into that direction. So it's all that meta learning and automated machine learning with meta learning is kind of cool stuff. Obviously, you even when we train our machine learning models, usually we try to do it in automatic way. For instance, when you deploy your main model, we train some complementary models that will monitor your main model, and it actually it's very challenging to do it in fully autonomous way. So you can just supply the data, you engineer feature automatically, and you basically choose the best model. So you should really put your training pipeline on autopilot, and this is kind of there are leaders in this space, but I would see that nothing. I would see more and more tooling in that will augment that training pipeline and make it not fully autonomous, but will keep the data scientist in the loop, machine learning engineer in the loop, by providing really cool dashboards and metrics, as I mentioned, TensorFlow but with more details and more information to make a decision. and also supporting other frameworks like PyTorch and Keras and others. So that's one direction. And another direction is just managing this enterprise workflow of accepting and approving the models to go to production, because we all like this agile style deployment of deploying stuff to production and managing it by engineers or machine learning engineers. But of course, enterprise workflow is much more complicated. So you can have some user testing, you can have some acceptance testing, and basically verification of by management team probably, or by business users, hey, that this model is ready to production. What I see, most of the enterprises are really required this. This could be done with classical software engineering tools, like CI/CD tools like Jenkins and whatever. But obviously, like machine learning will have its own specifics and its own metrics to be approved by business users. So and you see, this already goes to the business users, not to machine learning engineers level. So it's every machine learning model in some enterprises will need to be approved by business users and also to be compliant with all the regulations and so on and so on.
All right. Well, thank you very much for taking the time today to share your experience working on Hydrosphere and the overall state of affairs for managing machine learning in production. It's definitely a very complex topic, and one that is continuing to evolve as more people are actually getting to a point where they're leveraging these capabilities in their products. So thank you for your time and perspective, and for your work on Hydrosphere, and I hope you enjoy the rest of your day.
Yeah, thank you for the thoughtful questions. Have a nice day. Take care. Bye.